Okay, lesson 12.3, day 2, we're going to be talking about something called vector projections. Let's say that you've got vector A, which is designated down below vector PQ in this diagram, and also vector B, which would be vector PR, and there's an angle of theta in between. Let's call S the foot of the perpendicular from R to a line containing A. So go up to the head, the top of the arrow, the tip of the arrow, vector B, drop down a perpendicular onto A, and the point of contact we'll call S. The vector PS is the vector projection of B onto A, and it is denoted by projection lowercase subscript of vector A of vector B. So it's showing that B is dropped onto A. A is going to be the subscript. It's helpful to think of this projection as the shadow of B onto vector A. And what I'd like to point out immediately is the following. You can see that vector B is having its shadow onto vector A. In this case, vector PS, the shadow, is smaller than the entire length of vector A. However, if we would have drawn vector B to be longer than vector A, we could see that its projection would then be longer than vector A itself. Similarly, also, I'd really like to point out is if the angle between vector B and vector A were to be obtuse, if this angle was quite large, you'd see that the projection, the shadow, if you would, of vector B onto vector A would actually fall in the opposite direction of vector A. So I think it's important to point that out. Eventually, it is going to show up that could be the case. But let's talk specifics here about how to find this projection. Going back to our original picture here, let's call this shadow of vector B onto vector A, the projection of vector B onto A, x. Better yet, let's call its magnitude x. And right now, I think it's pretty obvious we could have a right triangle where we could say this is a length of x, here's theta, and here's a length of vector b, the magnitude of it. SOHCAHTOA should come into mind. It looks like we have adjacent and hypotenuse. So we'd have x all over the length of vector b would equal the cosine of angle theta. And more to the point, x itself would be the length of vector b times the cosine of theta. Now at this point you might be wondering, okay, so what's the point in all of this? Why are we finding this length of vector x? Here's what I'd want us to recall from our last lesson. Vector A dotted with vector b was equal to the magnitude of vector A times the magnitude of vector B times the cosine of theta. Now, I hope it's pretty obvious to you at this moment that this absolute value of B cosine of theta is right here. This thing right here is actually your shadow length. It's definitely going to be coming into play. So if we were to solve for that, if we were to solve for x, in other words, what you'd get is vector A dot vector B divided by the magnitude of vector A. So this is your projection length. And I want to point out that because we're just talking about a length, we don't have a vector, we're going to call this the component of B along A, and we're going to designate that as component of B all over A. A is in the subscript. Notice what we just found. A dot B, vector A dot vector B divided by the magnitude of A. I guess what I want to point out to you is that This is all onto vector A. It's like a shadow onto vector A. A is in the subscript, it's in the bottom. The magnitude of A shows up in the bottom of this formula as well. What is this exactly? It's the length of the shadow. It's the length of that shadow that we just found. So wonderfully, we'll just take the dot product of the two vectors and divide by the length of the vector that we're projecting onto, the floor that we're projecting onto. Now, of course, there's a world of difference between having just a length and having a vector itself. And that's why we're going to talk about the vector projection, not a scalar. The scalar projection is just one mathematical measurement without direction. A vector will also have direction to it. So we're still going to have this length of the shadow. But notice what we do. Vector A divided by the length of vector A is a unit vector, a length of 1, and it's a unit vector in the direction of vector A. So when you multiply the length of the shadow by a unit vector, that's when you can get the vector projection of vector B onto vector A. I think it would be helpful for us to take a look at a specific problem. It's really two parts. They're asking us to do a scalar projection and then a vector projection of vector B onto vector A. Before we go on, though, let's take a look at the length of vector A. If I know that I'm going to go onto vector A, that denominator is going to have to be the length of vector A itself. And that, of course, is the three-dimensional Pythagorean theorem of the I, j, and k components. 2 squared plus 2 squared plus negative 1 squared. That's 4 plus 4 plus 1. Of course, that's going to be the square root of 9, which is equal to 3. So let's go ahead and see if we can find, for part 1, the scalar projection of vector B onto A. And this is how we write it, just the component of vector B onto vector A. What was that exactly? Well, it's the dot product of A and B all over the length of vector A. Well, what is the dot product of A dot B? Well, it's the I components, 2 times negative 1, plus the j components multiplied together, 2 times 3, plus the k components multiplied together. And I'm taking the A component first. You very well could take the B component first. It's all commutative. The length of vector A down below is just a 3. So what we have here up on top is a negative 2 plus a 6 plus another negative 2. Negative 2 plus negative 2 is negative 4. Negative 4 plus 6 is 2. We'd get 2/3. What is this again? This is the length of the shadow. It's the length of the shadow. I'm not designating any direction whatsoever. That's for part 2. Part 2, when I'm asked to find the vector projection, well, that's something altogether different. First, I need the unit vector in the direction of A. So that's going to be vector A, which is 2, 2, negative 1. And I'm going to say divide that by a 3. So that becomes 2/3, 2/3, and negative 1/3. Okay, so I've changed this vector A by dividing by its length. This new length is 1. I could prove that with the Pythagorean theorem. Now, the projection of vector B onto vector A, plain and simply, we're going to take the length of the shadow, 2/3, and multiply it to this unit vector. When you multiply a unit vector which has a length of 1 to another vector, it's going to have a result of this new length. So my new length is guaranteed to be 2/3 because my overall vector length here is 1 for the unit vector. Final answer would be 4/9, 4/9, and -2/9. And now I have a vector that has a length of 2/3 and it's going in the direction of vector A. Taking a look at this other part, recall from last year we dealt with Hooke's law and we dealt with work, but we always had force along the line of motion. Force was always going in one specific linear motion, and you'd move a certain distance. Work was force times distance. But what if the constant force is a vector PR that's not along the line of motion, and the force moves from P to Q? This displacement vector we'll call D. That's the distance that we're going to be moving. Now from here, guys, what I want to point out is that X right here would be the length of the shadow. That would be the component of the force vector in the direction of vector PQ. So I guess what I want to point out again, if this is theta, we could, just as we did on the front page, say that cosine of theta is x all over the length of the force vector, meaning that x is the force vector times the cosine of theta. So this again is the component of the force vector in the direction of vector PQ. So now I have this force vector that's on the line of motion, the line of motion where we were having that distance moved. So this is the length of vector f cosine of theta times the length of vector d. If we look at that, we'll realize that's the definition of the dot product of the force vector with the displacement vector. So F dot D is work measured. Let's take a look at example here. A wagon is pulled a distance of 50 feet along a horizontal path. And you can see 50 feet's on the floor there. Constant force of 100 pounds, but the handle of the wagon is held at an angle of 30 degrees above the horizontal. Find the work done by the force. Well, we always have a choice. Either we're going to use the magnitude of F, magnitude of D, cosine of theta formula, or we'll use the actual dot product. When I'm looking here to find work done, I'm going to notice that I know that I've got force of 100. That's the length of this arrow. And I know that the displacement vector is 50. And then I'll just put in the cosine of 30. We all know that the cosine of 30, of course, is radical 3 over 2. And real quickly, 2 goes into 150 times. 50 times 50 is 25 with 2 extra zeros. So would you look at that? Our work would be 2500 radical 3. Wrapping up, in our very last scenario, we can say, what if work is given by a vector, 2i plus j minus 3k, and it moves a particle from point P 110 to point Q 521. Find the work done. Now we could find the angle in between, but I do want to say that D, we can always do end minus beginning. And we could say that that's, from the ending of Q, we'd go 5 minus 1, 2 minus 1, 1 minus 0. My displacement vector would be 4, 1, 1. And I already have a force vector, so work is just force dot D. Just go 2, 1, negative 3, dot 4, 1, 1, and you'll be done. I'll leave that to you to finish up. It shouldn't be too hard. you'll find work to equal 6.